Hello, this is the recording for 7th grade physics for Mr. Weiss on the 30th of April. And as people join in, hopefully they'll tell me hello and I'll know they're there and I can give points. If you're just seeing this video and you weren't there, please let me know that you've watched it afterwards, okay? All right, I see I got at least one person tell me hello, so I know you're there and who you are. Once we get enough folks here, we'll start up for the day and see what we're doing, see what our objective is for this hour. Okay, now I'm at the right time, so hopefully some others will join us here soon for the live stream. Again, if you're just joining up, tell me hello so I know who you are and I can give you points for attending. As soon as we get about half the class here, we'll start up for the hour. I still see one person. I'd like to say hello. Who is it? Well, my people are kind of late today. I see only one person on the live stream, and I'd like to ask that person to put in the little chat on the side who you are so I know who's here. And hopefully some others will join us. I believe I sent this out on 7D Physics. Let me just take a quick check. I did. I just checked it. So this is the right time. And you're at the right channel if you're tuning in. So I'm hoping others will join me very soon. If not, I'm going to do this just as a video and everybody will have to watch it. So we shall see. But I'd rather have most of you here because I like your participation. It'll be a little quiet just to talk to myself for the hour, but we'll do what we need to do. It's 9:39, so a couple more minutes and then we'll start up. Hopefully we'll have more people joining us very soon. I got a new whiteboard that's behind me, and I got some new markers as well, so I'm hoping you'll be able to see better this week also. That's my goal. Even a new eraser, so I'm just all prepared for you. Still waiting. I'll wait about one more minute as I would during class time. So then we'll start up after another minute. Is there really one person there? If there is, say hello so I know who you are. Tap your name on the side comments, please. Okay, well, I guess I'm going to do this as a video. So here's the deal. Today we're going to take our data from last time when we measured some of these objects, right? And we're going to graph them and figure out how to find the the density from a graph and see what relationships we can see by graphing. I'm doing this for a number of reasons, but one reason is that the experience we have in physics is that younger students don't tend to be able to graph very well. And I want each of you to have that skill and be able to graph before you go on to 8th grade. So I'm going to show you my graph, and I'll kind of bring it up close, back and forth so you can see it. Here's my graph. So it's got mass and volume, and we're going to plot the points we had last time. I put them down below, but you have those data points already. And so we're going to graph those, okay? So find your graph, find a pen or pencil. Actually, pencil's better, but I've only got a pen with me. I like to do pencil in case I make a mistake. And yeah, we're going to do our graphs together. So make sure everybody does it correctly, okay? Again, let me know you're here. I see 3 people. That's good. Tell me who you are. And I can give you points for being here. All right. Still silence from you. I'm not sure why that is. Let me make sure my... Oh, now I'm getting some people. Good. I've got Aaron and Jonathan. Thank you both. Thank you both for checking in. Okay, I got another person. Maybe they'll join us as well. But let's go back and start our graph. So on our graph, we need to kind of look at our values. And if you look at the notes, I hope you have from last week, because we need all your grams and milliliters from last week. If you look at the mass, our biggest mass is 138.94. And what we've got to do is, for 138.94, we've got to figure out how big to make our graph. So I'm going to go on the mass side, and I've got to decide how I'm going to fit that. Well, 138, I could do that as like 14 boxes, where each box could be 10 grams. Let's see if that's going to fit. So there'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. That's going to fit. Now, I could do 2 boxes, but then I'm going to be off my graph. So it looks like the scale, as we call it, is going to be, well, I'll start with 0. So put a little line for 0 grams. And then I'll put some lines maybe every couple of lines, some numbers every couple of lines. So if we decided on every box is worth 10 grams, then I'll just do 2 boxes, and I'll do 20, 40, 60, 80, 100, and I wrote too big, but I'll try and squeeze it in here. Put in some numbers. You don't have to put in every line, but just enough so people are there. Lisa's here and Yo is here. Thank you both, and welcome. Super. Okay, where was I? Yeah, so I'm at 100, 120, and 140. I can go past that, but I don't really need to. Okay, now let's look at the other side, all right? So the other side, so that's the mass. So we've got room now up to fit our biggest mass. For the volume, those only go up to what? Our biggest one is 50. So for 50, I don't want to use I don't want to use 1 box, because that would be silly. 10, 20, 30, 40, 50. Then the points are here. I want to spread my points out when I do physics. So let's see. If we got 50, we can do like a bunch. We could do for 10, we could do maybe like 5 boxes. Let's see if that's going to fit. 1, 2, well, here's 0. And now we're on milliliters, right? That's the bottom volume. I know you can't see this very well. I will hold it up as soon as I get the numbers in, okay? Okay, so then I'm going to do 5 boxes. 1, 2, 3, 4, 5, and that's going to be 10 milliliters. Then 1, 2, 3, 4, 5. It's going to be 20. 1, 2, 3, 4, 5. 30. Oh, 1, 2, 3, 4, 5. 40. 1, 2, 3, 4, 5. 50. Okay, let's have a look at this. All right, so here we go. Oh, and Stephanie is here. Hi, Stephanie. Thank you. Good. Okay, so I'll try and hold this so you can see it. So notice my numbers here. So on this side, I've gone like just every box is a line. So I got what, 20, 40, 60, 80 up to 160 or 140, 140. And over here for the volume, my biggest was 50. So I went 10, 20, 30, 40, 50 milliliters, and that covers that. Why did I do it this way? Because I want to spread my points out and fill the whole graph. And notice I'm doing my graph like on about a half a sheet of paper. So that's really good. You want to, don't make your graphs tiny. Emil is here. Thank you, Emil. Good. Thanks for checking in. Don't make your graphs tiny. So we made our graphs big, okay? So once again, for Emil, we're going to do on this side, for every box, it's 10 grams. So 10, 20, 30, 40, blah, 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 up to 140. And for this, it's every 5 boxes we picked for 10 milliliters. So 5, so 10, 20, 30, 40, 50 to spread my points out. Now let's graph those points. So I'm going to invite you to graph them as well. What we're going to do, I'm going to do the first one because I want to show you how we do it in physics, all right? I'll show you in a second. I know it's hard because it's small. The first one was 138.94, so I'm going to go up close to 140. And the second one was 50 milliliters, so I'm going to go over to the 50 milliliter line. And it's on that line, but it's almost high enough to be the other one. So I'm going to put a line here. Now, there's my point. I'm going to do it the German way. The German way is little x's, okay? And I want you to do that with your other 3 points as well. So take all 4 points now and please graph them, and I'll do the same. So I've got one of mine done. And do yours. Maybe you've done it already. I don't know. If not, let's go ahead and do them. Okay, so my second is 89.91. So there's 60, 80, no. 60, 80, 90, it's close to 90, and 27 is close to 30. And 30, so it's a little less than 30, maybe about there, and a little less than 89, but not much. So it's just about on that line for 90. So it's a little less here, so it's going to be like right there. Right there. Okay? And my third one, 16 and 6. So 16 is just here, 10, 20, 16, and 6. What was it? It was 2, 4, 6. So it's on this line, and 16 would be just a hair above 15. And then my last one was 23 and a half about, and no, it was 62 and 23. 62, and there's 20. So 22, 23, a little more than that. And what did I say? 62, so a little higher than 60. Okay. That's not bad. Okay, so here we go. Once you got your 4 points, I'm going to show them to you. And I got what, 1, 2, 3, 4, 5, 6. I got 6 of you, but it shows 7 or 8 listed. If you haven't said hello, please say hello so I know you're here. So your graph should look something like this, all right? UCN is here. Thank you, UCN. Okay, so check your graph of mine. You should have 4 points with 4 x's. They should pretty well line up. If they don't, you might have made a mistake. Good. Now we're going to take a ruler. So if you don't have one, run back and get one. And we're going to take our ruler and we're going to line it up. We're going to go through 0, 0. And then we're going to do what's called, Tully's here. Hey, I'm glad you're here this week. Okay, Tully, thank you. Line up your ruler with the 0, 0 line, and then you're going to kind of put it through the middle of your points. That's called a best fit line. We're going to write that on our graph in a second too. So I started 0, 0. I'm going to go through the middle of my points. I have to estimate that. So don't just connect the dots. Instead, put a line through the middle. And there's my line. So this is called a best fit line. And that was our line for aluminum. Okay, so I'm going to show you this for a sec and let you maybe catch up. And I'm also going to write some of this on the board in bigger markers so you can see this now. All righty, so that's what I want you guys to do. And again, a best fit line, so put your actual ruler here and make a nice straight line through the middle of your points. It may not touch every point, that's okay. All right, just do your best, go through the middle of the points. That's called a best fit line in physics. So I labeled it up here, best fit line, and I labeled what it was, aluminum. Good. I'm going to put that over at the bottom here for a second. You can still see it if we need to. And I'm going to write that a little bigger here now. So my line looks something like this. And that was aluminum. And this was mass in grams. This was volume in milliliters. Yeah, that looks bigger, so you can see that. Good. This again is called a best fit line. And you should have some little X's either on it or nearby. So I had some X's, they weren't quite on it. They were like there, I don't know. Something like that, okay? So I went through the middle of my X's. Somebody else rolled in, so let me know who you are. In the meantime, yeah, let's talk about some stuff. I've got now, instead of aluminum, I've got some plastic. So plastic, what do you think? It's going to be more dense or less dense? So just type in an answer. Plastic, more or less dense than aluminum? I got less, and you're all correct. Good. So it's going to be less. So let's say I took parts of this and got the mass and volume, so I'd get a bunch of points maybe from types of aluminum. And my question to you is, if I plotted these points, where would these points be on the graph? Would they be like steeper than this graph or less steep? So where would the points and then the line be for plastic compared to this? Think about it. So steeper or less steep? What do you think would be the case for plastic? Steeper line or less steep line? Got a guess already? Let's see a couple more guesses from you. Appreciate your participation. And Emil, Stephanie, and Jonathan, you are right. It's going to be a less steep line. So what's going to happen is, because plastic's not as heavy per piece, we say it's got less volume, or sorry, less mass, but still a certain amount of volume. So it's going to be a line down here. I don't know where. I'm just going to draw a line, an imaginary line, and right here, plastic. And we're going to write less dense. Let's do a third line. Can you guys guess me something that is more dense than aluminum? What's something you think, oh, I think that's pretty dense stuff, either in English or German, something more dense than aluminum? And then we're going to put another line for that. And there's more than one answer. Emil says stone, and the answer to that is yin. Some stones are more dense than aluminum, some are less, so it depends on the stone. Same with rock, same with granite. Steel is probably a little denser. Jonathan, that would work. How about another metal that somebody knows that's pretty darn dense? Granite may or may not be denser. Being a geologist, I'll tell you, it's not probably a lot different than aluminum. I studied geology. Iron, yeah. Titanium, that one I don't know. Iron looks like from UCN. Yeah, that'll work. Okay, so iron's probably a bit denser. There's one that's a lot denser. And we sometimes say it in English, wow, that's heavy as heavy as and it's a type of metal that's rather dense, or heavier than a piece of starts with an L. Again, iron might work, copper might work, I just don't know. Bronze, that might be true too, that's probably denser. No, the one I was thinking of is lead, or Blei in German. So let's do another line for that, okay? As you could guess, our other line's going to be steeper. So I'm going to say, okay, compared to aluminum, lead is just way steeper. So I'm going to draw a line there and write lead. And that's going to be a steeper line. Okie dokie. And Tilly is here. Super. Thanks for checking in. Anybody else here, please check in. Okay, I want to do something with our graph now because we spent so much time using it. And now I'm going to use the real graph to do this. And I'm going to say to you, let's see, what if I had, look at our numbers over here, okay? What if I had, my original data is 138 grams, 89, 16, 62. What if I had a piece of aluminum that was exactly 100 grams? What would the volume be? I'm going to write that question. So if 100 grams of aluminum, Al, you might know that's the symbol for aluminum. That's okay. Thank you, Tilly. Okay. What's the volume? And the answer is, we can use our graph, our real graph, to find out. And we're going to do that in a second. So use, and here's the name of the skill we're going to learn, interpolation. And interpolation is a fancy word which means use your data to help estimate. Is estimate the word I want? Let me think. Use our data to predict. That's the word I want. Use data to predict. That's how we do a lot of things in science, okay? We may not be able to go to Mars, but we can predict how it might happen, okay? Let's try that. Okay, so here's my graph. You caught up there? So interpolation, use data to predict. That's what interpolation is. Okay, so we're going to do this with our graph. So take your graph, and I'll show you up close what I'm doing in a second. And you're going to go to 100, and then you're going to take your ruler and make a line horizontal until it hits your graph, okay? 20, 40, 60, 80. There's my 100 line. Okay, so here's what I've done so far, okay? So take a look. I went from 100, and I want to use my line, so I drew a line over to my data line, and I circled that spot. That's what I've done so far. Now I'm going to go down. I'm going to draw a straight line down and see where it lands on my horizontal axis, my x-axis, okay? That's interpolation. So go ahead and do that. I'm going to do the same thing. And one person answered already, and that was Aaron, but let's see if others can look and see what they get. Where does yours land on your graph? So when you interpolate, that's the verb, where does that sucker land? On what volume? If my block was 100 grams in mass, it should take up what volume? See if yours matches the same guesstimate as Aaron had, for example. So I'm putting that close so you can see what I did. This is typical over and down to interpolate. Yo's got the same thing. Let's see if a third person does as well. Emil does as well, and so does Tully. Great. So let's just write that. Hey, it was, what's the volume? I'm going to write it up here because I've run out of whiteboard space. So the volume was, I'll say with graph, V was equal to 36 milliliters, ml for what the volume is. Yeah, that's really important stuff. Do you guys have any questions about that? Because we're going to move into something related to that density here in just a minute. So you used interpolation, you used a graph, and you notice that, oh, actually we should be, here's what we notice. Okay, for aluminum, for our data, for aluminum, aha, the greater the volume, that's the x-axis. We usually talk about that first. The greater the blah. So you're going to fill in the blank now. So let's see if I can, I know that's in the shiny part. Let's see if I can make it less shiny. There you go. So for aluminum, the greater the volume, what did we prove? The greater the. So can you fill in the with the correct word? So type it in and give me a little feedback. Aaron's got it already. Let's see if a couple others can get that word. And Lisa and Stephanie, super good. And it is the greater the mass. So this is called in math class a direct relationship. Everybody's got it. Good job, everybody. So it's a direct relationship. When one thing goes up, the other goes up. And it's also called a linear relationship. Why is it linear? Because it made a line, okay? So I can even write here up at the top, this is a linear relation or relationship. That's a good thing to know. So a little overlap between math and physics class, okay? Linear relationship. When one goes up, the other goes up. It's true of a lot of things in the world. So it's a good relationship to be able to understand and to be able to really clearly graph. If you can do that, you're going to be ready for 8th grade. That's a big skill. Even some of my 8th graders, I got to help them because they're not so good at it. But if you are, that's great. Okay, I'm getting my eraser ready. And I'll tip the board again so you can see all the stuff I wrote, I hope. I know it's shiny in here. I'm just trying to get as much light as I can. Okie dokie. Here we go. I got to stand up because then it's nice, thorough erasing. All right, I got it. Yo, okay. All right, so I've got a question. We've got still more to talk about with density, but before we do, how are we doing on time? We're doing okay. Before we talk more about density, I want to ask you a question about the assignment I gave, okay? I know for some of you it was hard to get into that simulation program. So either A, I talked to Mr. Blessman about this, you either got to download that Flash player, or B, try and use the function on the website that says embed. I tried it back and forth and I finally did get in and I was able to use the program. So see if you can do that as well. Maybe get help from a parent or older brother and sister if you still have trouble doing it. Can you just give me a quick count? How many of you of like what do I got here? 9 of you? 1, 2, 3, 4, 5, 6, 7, 8, 9. How many of the 9 have gotten into that program? How many of the 9 have gotten in? Just punch and write in if you've gotten into that simulation program. I know a couple of you did finish, so I know some have gotten in. Okay, I got 1. I got 1 that did not. Julius just joined us. Thank you, Julius. And the question we just asked Julius was, did you get into the program yet? Okay, Lisa writes, it worked on the PC of my father. Okay. So let's see, I got about 1, 2. It did not work for a couple others. Okay. Yo, it did not as well. So I only got like 2 or 3 of you. If you have a class chat, you may want to talk about this with each other and try and help each other get in. I'm not a perfect whiz with computers, but I did get in without downloading Flash Player. So maybe talk to each other about it and try it again. okay? And Julius writes a lab worked for him. So I got about three or four of you where it worked out, okay? And I had another one or two people email me that said it did work. Totally can't get in either. Okay, so try again, try the embed button and see if that will help you, okay? If not, you may want to try and download it on some PC in your family, if you can do that. If you absolutely can't do it, that's the way it is, okay? I can't be there for you, unfortunately, to do it for you. So if you can do it, great. If you can't, that's the way it's got to be. But it's pretty cool to play with, and you'd learn some neat physics. So I hope you can do this assignment. I hope you can get in. The other thing you can do, is call a friend who can get in, and you can see some of these people. Yeah, it's spelled like that, Jonathan, embed. Call a friend who has gotten in and have them kind of do the lab again with you. They can open it up and tell you what it's looking like and what happens. It's more or less looks like a bathtub, and you take different blocks and put them in, and you get the volume, and you see whether the blocks float or don't float. And you can also get the blocks and measure their masses over on a scale. So it's kind of similar to what we did if you were here the first time last week, okay? Yeah, so that word again is, well, embed. You can see it on Jonathan's comment there. Okay. I want to talk about water's density. Because our planet has like 2/3 of it's covered with water. It's really important stuff. So the density of water has a certain number, which I want you to know. Like, for example, for aluminum, if you were here last week, we had like 2.6, 2.7. Water is very different. Okay, so water, the density, and here I'm going to write the formula again. Density is mass divided by volume. I should ask you that. Sorry. And for water, I'll write D of water, density of water. It's 1.0 grams per milliliter. Exactly one. Aluminum, I'll write up here, was about 2.7. That's what we got, close to 2.7 grams per milliliter. So water's a lot less dense at 1. Water was chosen as the starting compound in this case. So it's not luck that it's 1. It's exactly because they started with water and they said, okay, we're going to make water 1. Okay, we're going to make it 1 milliliter. We're going to make it 1 gram, and based on what a gram. Okay, sorry, backwards. They measured a cubic centimeter of water, and they weighed it, and they called that weight 1 gram. So everything's based on water because it's really important for our planet. So that's kind of like the starting number, okay? All right. What happens if I've got something less dense than water? And I'm going to pull something out from underneath the laptop. Hold on. Look what I got. Piece of styrofoam. So somebody help me out. I throw that in water. What's it going to do? I throw that in water. What's it going to do? Thank you, Stephanie, Lisa, and others. Good. I'll put that back where I can use it. It's going to float. So if less than 1 gram per milliliter, object floats. And of course, the object I held up was styrofoam, right? Styrofoam. And if it's greater, of course, than 1, then it sinks. Those of you that have done the lab, or you know from your own experience, anything that's denser, if I throw it in water, bloop, it goes to the bottom. A stone, a piece of um, metal. Yeah, not everything, but a lot of stuff goes to the bottom. So if it's less than 1, it goes to the bottom. Okay, here's the weird thing. We talked about phases, right? Remind me, what are the main 3 phases? Can somebody give me those so I know we remember what those were? That's when I still saw you in person. The 3 phases of matter are blah, blah, blah. What are the 3 phases of matter? Tully, you're quick on the draw. Solid, gas, and liquid. Good. Can you guess which one of those 3? And thanks for everybody for responding. Tilly's responded too. Which of those 3 is generally the densest? Which one is the densest? Or you can also tell me in words which one is the least dense. So the densest could be solid, good, and the least dense would be, you kind of remember this when I had you act this out, right? When were you least dense? You were least dense when you were, thanks Julius, right? When you were a gas and you were all spread out. So here's how I can write that. The density of solid is greater than, right? Like in math class, greater than symbol is greater than the density of liquid. I'm going to write LIQ for liquid, which is greater than the density of gas. And that's true for just about everything, except for one thing. Who knows the exception as you're catching up? Anybody know the exception? Because it's an important exception and we got to talk about it. No guesses? Okay, so it's like in German, the exception proves the rule. Well, we got a really important exception. So the exception, I'm going to write this in red. Anybody know yet? No. It's what I call weird water. Huh? Why? Well, think about it. If I got a glass of water, let's say it's a hot summer day, and I throw in an ice cube is solid water, right? Ice is solid water. Does the ice cube go to the bottom? No, it floats. So there's my ice cube. Ice, which is just solid water, floats. So water is weird, okay? We don't have to go into details about the chemical structure, but you can probably just about guess what's going on, okay? If I have a bunch of water molecules, okay, here they are as a liquid, well, somehow when they form a solid, they don't get closer. Remember how you guys got closer when I had you go around the classroom, and you got a little closer? They don't do that. For ice, when the ice forms, the molecules actually go apart a little bit and then freeze. And they're at the perfect distance apart from each other to form ice. So it's a weird but important exception. And it turns out it has some environmental ramifications, some environmental applications, which we need to talk about next. So exception, so I can say that the density of water, liquid, is actually greater than the density of water, solid, which is, of course, what ice is, if you think about it. So mighty strange. Okay, and again, it has to do with the crystal shape. The crystals of water are just bigger. In fact, you might have noticed this. If I freeze, here, I put some water in an ice cube tray. Ready? Blah, 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 blah. Okay, I put the ice cube tray in the freezer. I come back later, and what happens as the ice forms? Who's noticed this? I put water in there. I come back later and look at the ice cubes, and what has the water done while it's frozen? So ice cube tray, water. It's crystallized, yes, but something else has happened to it. I put in the water. I come back later. What do you notice about the ice cubes? Lisa, they've spread out. Yes. How do you mean, Lisa? What's happened to the volume? Yes, you're all right, Tilly. Yes, it turns into a solid. But as it turns into a solid, what does the water do? Starts with an EX. It's bigger, Lisa, more volume. Exactly. Good. Okay, so I'll write here ice, or no, let's write water. Water. And if you've never noticed this, do it at home, okay? Expands, expands. Good. So now you guys have got it. Okay, so water expands when you freeze it. You don't believe me? Hey, when we're done with this lesson, go put like some water in an ice cube tray or something else your parents won't get upset about. Put it in the freezer and remember how it looks, and then come back later and measure it, and it's going to be bigger. It's going to be a bigger volume. This is the way it is. So ice floats. Ice floats. Well, you might say, okay, Mr. Weiss, that's interesting, but so what? Okay, let's come to the consequences now. Once I let you catch up with your writing here, let me tilt that so you can see, hopefully, everything I wrote. So I just wrote, water expands when you freeze it, and density of water is liquid is greater than density of water as a solid. Okay. Whoa, hey, good catch, huh? Let's try it from sitting. See if I can do this. Yeah, not too bad. Okay. An application is where you find it in technology or nature. So this is an application of that idea. It's called turnover. In lakes. Okay. I've been in Berlin 19 years, and when I first got here, every few years the lakes would freeze over. That hasn't happened in a while. Maybe some of you have never seen a frozen lake. I hope you've been somewhere where you've seen a frozen lake. And of course, when you have a frozen lake, is it frozen all the way to the bottom? When you have a frozen lake, is it frozen all the way to the bottom? You got it. Yeah, UCN and Tilly and others have got it. Yo's got it. It's only at the top. So what happens is, obviously, the ice is less dense. So like we said, it's at the top. But I want to talk about 2 times a year. One is in like March, in spring. So turnover in lakes that freeze over. If they almost freeze, it'll still do this. Okay, it'll still do this. So here, draw yourself a lake. And this is going to be in spring. And we call it spring turnover. Okay, so here's your lake. Right after the ice melts, the temperature up here is around maybe like 1 degree. The temperature at the bottom of the lake might be more than that. Maybe at the bottom of the lake, it's not, because it's not right by the ice, let's say it's like 4 degrees. However, here's a little thing we got to know. Ice or water is densest. How are we doing on time? We got 2 more minutes. It is densest at 6 degrees C. So that's when it's a liquid, and especially at that temperature, that's when it's densest. So what happens in the spring is the sun shines, right? And what warms up first? Well, of course, the top of the lake. The top of the lake warms up. So I'm going to erase the 1 now. So that'll be warm sun. And maybe it warms up to 6 degrees. Once it warms up to 6 degrees, what's the 6-degree water going to do if it's the densest at that temperature? Hint, think of the name, turnover. What's that 6-degree water going to do once it gets warmed up to that temperature? Any guesses? What's the water going to do up here, the 6-degree water? When it hits that temperature, it's all liquid, okay, Julius? So 6, 4, it's all liquid, but this liquid is denser. It's the most dense then. The ice is all gone. There's no ice anymore. It's all liquid, folks. The ice, the spring turnover, okay, the ice is densest at 6 degrees, okay? It's already melted, and now the stuff, not only is it melting, but the water that is no longer ice is warming up. So now it gets up to 6 and it becomes dense. It's the densest at that temperature. It's denser than the 4-degree water at the bottom. It's not going to evaporate, at least not much. Lisa's got it. It's going to go down. So it's going to go down here and replace the 4-degree water. And the 4-degree water goes up to the top. That's why it's called turnover. Okay, the water turns over. And it keeps doing that until all the water is 6 degrees. So I'll say, so we say the lake is turning over as the dense 6-degree water goes down. And then the cooler water comes up. I'll say the cooler water, you still see that? Yeah, rises. Isn't that kind of cool? That's really important for what creatures that are in there. Oh, we're over time. Okay, so next time let's talk about, so why important for fish and plants. I'll let you think about that for next time. We'll answer that then, okay? Thank you for participating, everybody. And try and help each other on the program. See if you can get into that thing. And we'll talk more next week. I'll send you probably the same time next week, but I'll send you a message about when our next live stream would be. So thanks, everybody. Thanks for participating. Bye-bye. Have a good long weekend.